Hello everyone, my name is Anish Baladevan. I'm a mechanical automobile engineer. I'm currently serving as a project manager with L&D Technology Services, and I have worked for major automobile players like Honda passenger cars, Scania trucks and buses, Tata Motors, Proterra electric buses, etc. I'm currently on deputation at Honda North America, but more than my titles, I'm a man who has lived and raised the evolution of the machine for over 18 years. I have spent nearly 2 decades in the research and development trenches, obsessing over the physics of motion and the chemistry of energy and the cold, hard economics of global supply chain. I have seen the blueprints for the engine that defined the last decade, and I'm currently looking at the data for the vehicles that are supposed to define the next one. In 2020, the automotive world made a grand, sweeping promise to the public. We were told that by 2026, the very year we are living right now, the internal combustion engine would be a museum piece, a relic of primitive, carbon heavy past. We saw all in commitments from boardrooms in Detroit, Tokyo, and Stuttgart. We saw multi-billion-dollar EV pipelines established with a zeal that suggested translation to battery electric vehicles or BEVs was a simple, inevitable sprint to a finish line. There was a sense of electric euphoria in the air, a belief that if we simply built the cars, the world would fundamentally change overnight to accommodate them. But as we sit in here in 2026, the industry is waking up to what I call the electric cold shower. The global automotive landscape has reached a volatile crossroads. In North America, growth hasn't just slowed, it's stuttering. In Europe, the early cooling of consumer interest has turned it into a deep chill as subsides vanish and the reality of high energy costs sets in. We have seen giants, companies with a century of engineering pedigree, forced into painful multi-billion-dollar strategic retreats. They are slashing their EV pipelines not because they want to, but because they have to stem a level of fiscal hemorrhaging that threatens their very survival. The all electric dream has collided with three harsh, unyielding realities: infrastructure gaps that refuse to close, a fragmenting geopolitical theater of trade wars and tariffs, and a consumer who is, quite frankly, exhausted by the pure EV or nothing narrative. My 18 years in R&D, spanning everything from a nimble passenger cars in your driveway to the heavy-duty workhorses that haul the world's freight, led me to a definitive, perhaps controversial conclusion. The path to true decarbonization is not a fat sprint towards a pure battery finish line. It's a sophisticated, pragmatic engineering pivot towards what I call the in-between. Let's start by saying this clearly. I do not hate the electric internal combustion engine. I have spent my life in the lab, on the test bench, and on the road, tuning combustion, optimizing efficiency, and measuring emissions. I have watched the same engine evolve from something that was dirty, inefficient, and noisy into a quiet, lean burn marvel that can sip gasoline while still pulling us forward. In 2020, the narrative was simple: ban the engine, build the battery, and the world will heal. Cities started talking about zero emission mandates. Governments drafted legislation that aimed to phase out the internal combustion engine by mid of 2030s. Automakers, eager to look bold and visionary, announced multi-year EV roadmaps. That sounded more like a marketing brochure than a feasible strategy. And yet, by 2026, the data is piling up. In Europe, the European Automobile Manufacturers Association shows that EV sales growth has plateaued, and some countries started a decline as state subsidies pulled back. In Germany, where Bavaria once led the charge of electrification, you now see dealership lots full of discounted EVs sitting unsold for months. In North America, the big three automakers have announced project cancellations, plans idled, and billions of dollars in write downs. These are not oops moments. These are systemic corrections. They are the sound of the real world catching up with a PowerPoint. The public narrative have framed this as a moral choice. If you care about the planet, you buy an EV. But engineering does not operate on moral slogans. It operates on maths, physics, and constraints. And when we look at the full system, the mineral supply, the grade, the climate, and the human behavior, we see something very different from the fairy tale the world has sold in 2020. To understand why the in between is the only logical path forward, we have to talk about the math of resource scarcity. As engineers, we are trained to optimize systems under constraints. We do not live in a world of infinite lithium. We do not live in a world of infinite cobalt or nickel. Every gram of rare earth metal we pull from the earth has a carbon cost and a geopolitical cost. When we talk about the transition to green energy, we often act as if the battery is magical, weightless, and cost free component, but it's not. It's the most resource intensive part of a modern machine, processed in a handful of refineries and assembled in a handful of factories. That concentration is not just economic. In fact, it's a geopolitical vulnerability. Let's look at a real life R&D metric that has recently become very pragmatic engineering. The 1-6-90 rule. This isn't just a clever slogan. It's a fundamental of resource allocation backed by internal studies at one of the largest automakers in the world, Toyota. Toyota's senior scientists have published this exact analysis, showing that the same lithium used for one BEV can be allocated for 6 PHEV or 90 HEVs, with a hybrid fleet delivering up to 37 times more carbon dioxide reduction over the lifetime. Imagine you have limited supply of minerals, the mineral bank, if you will. If you take the minerals required to build one massive 100 kilowatt hour battery for a single long range high performance electric SUV, you have effectively taken one internal combustion engine out from the board. Yeah, that is one to one win on paper. It looks like progress, but as someone who manages complex engineering projects, I ask, is that the most efficient use of the mineral bank? If you take that same amount of material, you could instead build 6 plug-in hybrids. These are vehicles that can do over 40 miles of daily commuting on pure electricity but have a small engine for longer trips. Or if you prioritize mass market impact, you could use those same minerals to build 90 traditional hybrids. Now, let's do the math for the planet, not for the marketing department. One person driving $70,000 electric truck reduces a certain amount of carbon dioxide. Yeah, that's true. But 90 people driving hybrid sedans that get nifty miles per gallon, displacing 90 older, thirstier gasoline cars reduce far more than total carbon dioxide. In fact, the math shows that the 90 hybrids reduce about 37 times more carbon than a single BEV. When we prioritize pure solution for the few, we ignore the effective solution for the many. In a world of resource scarcity, 90 small wins will always defeat one big trophy. Now let's bring this down from the laboratory to the driveway. Picture a family in a rural Ohio, not unlike the one I see every morning on my way out of Columbus. They own all pickup trucks that gets 15 miles per gallon. Every winter, that truck guzzles gas. They hear the news about EVs, but they live in a mobile home um, with no charging station. The nearest fast charging station is like 30 miles away. Now, imagine the same family gets a hybrid. Not a fully electric fantasy car, but a boring, practical hybrid sedan that gets 50 miles per gallon and can be fueled in 2 minutes at any gas station in the country. That one car doesn't win awards at auto shows, but it replaces an old, thirsty car and reduces fuel consumption by two-thirds. Over the next 10 years, that family will pump thousands of fewer gallons of gasoline into the tank. That's real decarbonization. This is exactly what 1-6-90 rule is trying to capture. It's not about purity, it's about scale. It's not about a few affluent buyers who can afford a 70 kilowatt hour battery pack. It's about millions of families who need to drive every single day and cannot wait for a utopian charging infrastructure. In India, the world's second largest car market, hybrids still have exploded while EVs remain niche. In 2024, Toyota's hybrid models alone accounted over a third of the company's sales in India, and total hybrid ownership in the country has crossed 1 million vehicles. These are not feel good cars, they are workhorses that save money at the pump and reduce emissions by double digits compared with their older counterparts. In Europe, cities like Oslo and Amsterdam were once spotted as EV utopias, but even there, the data is shifting. In 2025, the analysis by the Norwegian Road Federation found that the average TCO, total cost of ownership, for a mid-sized EV in cold weather conditions was significantly higher than for a comparable hybrid, especially when you factor the charging penalties, battery degradation, and winter range loss. The same pattern is emerging in Germany, France, and the UK, where hybrids are quietly outselling pure EVs in mid-price segments. The in-between is not a compromise. It's a workaround that actually works. It's the engineering equivalent of wearing hard on a cold morning instead of trying to redesign the entire atmosphere. Now, let's talk about the physics of what I call the gold call gate. I live and work in Columbus, Ohio. In the R&D world, we don't just test vehicles in sunny California. We test them in the real world. And the real world physics are harsh mistress. In an R&D lab set to 77 degrees Fahrenheit, a lithium-ion battery is a miracle of efficiency. Yes, but it holds charge beautifully and delivers power with precision. But take that same battery to a parking lot in Ohio during January blizzard, when the temperature drops to sub-zero, the internal resistance of the battery rises. The chemical reaction slows down. The battery thinks slower. This isn't just about rain, this is about charge gate. In sub-zero temperatures, the battery cannot accept a fast charge without damaging the cells through lithium plating. To protect itself, the car's computer throttles the charging speed. A 20-minute stop becomes a 90-minute ordeal. A study by the American Automobile Association shows that at 20 degree Fahrenheit weather, some EVs can lose 10 to 12% of their rate and range just from the cold, and 30% or more when the cabin heater is turned on. Another analysis by Rucker and Doro shows that in extreme cold, the same vehicle can see charging times triple, turning a quick pit stop into a major schedule disruption. In the lab, you can rewrite the rules, but in the real world, you cannot. Now, turn to hybrid. In hybrid, the internal combustion engine is not a backup. It's a thermal battery. When the car starts in cold weather, the engine warms up, and that heat is used to warm the cabin and critically to keep the traction battery is in its optimal temperature window. We are using the waste of one system to solve the failure of another. That, my friends, is engineering excellence. In Columbus, in Fargo, in Montreal, in Stockholm, cities that live with winter, the hybrid is not a half measure, it's a rational choice. It delivers the electric driving experience where it matters most low speed, stop and go traffic, while gracefully falling back on the engine when the battery is cold, depleted, or being asked to do something that physics simply will not allow. I have colleagues at major OEMs who run winter testing in places like Scandinavia, and they constantly tell me the same thing. The hybrid works. Not because it's perfect, but because it respects the laws of thermodynamics rather than ignoring them. The data from places like Minnesota and Canada shows hybrid penetration growing steadily in climates where the winters are severe. Because people are voting with their wallets, not with their environmental aspirations. Now, let's move from the family sedan to a heavy duty sector. The Class 8 trucks that are the lifeblood of our economy. I have spent a significant portion of my 18 years looking at the duty cycles of these machines. A long haul trucker operates on hour of service clock. Every minute a trucker isn't moving is money lost for the entire supply chain. A diesel truck. It can refuel 300 gallons in 10 minutes, giving it 1500 miles of range. That's not a luxury, it is a business necessity. To match that with a pure electric battery today, the truck would need a battery pack weighing nearly 10 tons. Let that sink in. 10 tons of weight is equivalent of 5 Toyota Corollas. That is weight that is in cargo. It's weight that puts massive stress on the bridges and roads. More importantly, it is dead weight that requires more energy just to move it. This is the EV weight paradox. By adding more battery to get more range, you increase the mass, which requires more energy, which requires more battery. We are chasing our own tails. A 2019 study by the Swedish research group OMEV analyzed advanced battery electric long haul trucks and found that a truck designed for 800 kilometers of range would need a battery storing about 1400 kilowatt hour of energy, weighing roughly 7 tons. That cuts the payload by around 30% compared with a diesel counterpart. In other words, to go the same distance, the electric truck must carry less revenue than rating cargo. In a business built on margin, that is a non-starter. Now, watch what happens when we introduce in between into the sector. A hybrid range extended electric truck keeps the electric driveline but downsizes the battery and pairs it with a small, efficient engine that only runs when needed. That hybrid or range extended architecture breaks the cycle. It gives us the efficiency of an electric drivetrain without crippling the mass of 10-ton battery. In Europe and North America, companies such as Volvo, Daimler, and even new entrants like Scout Motors are experimenting with range extended electric architectures for heavy duty vehicles. These are not fake electrics. They are pragmatic solutions that recognize the physical and economic realities of trucking. A 2025 NACFE study in electric semi trucks found that while full battery electric trucks can work specific duty cycles, hybrid can range extend architecture remain the more viable path for a long haul operator where range, payload, and charging time are critical constraints. Where a trucker can pull into a truck stop, refuel in 10 minutes, and continue their run. That's not a compromise solution, that's a working solution. That is engineering that respects the real world. Then there is an issue of almost no one talks about the zero emission conversation. The hidden cost of tires. EVs are heavy. A typical electric sedan can weigh 1,000 pounds more than its gasoline equivalent. That weight has a hidden cost tires. We are seeing real world data in 2026 showing that EVs eat through tires 30 to 50% faster than internal combustion engines. Why? Because electric motors deliver instant torque and heavier vehicles put more mechanical stress on the rubber. Those tires are made of petroleum products. When they wear down, they release microplastic into the environment. In 2024, a study published in the Journal of Polymer and Plastic International on the tire-induced microplastics estimated that EV-induced tire wear is already significant secondary source of microplastic pollution. And this flow will grow if the weight of the EV continues to increase without corresponding improvements in tire technology. Engineers who focus only on tailpipe are blind to full the picture. The in-between does not ignore this, it engineers around it. By keeping the vehicle lighter and the battery smaller, we reduce rolling resistance, tire wear, and the downstream pollution that comes with it. We are not ignoring the second and third order effects. We are designing our way around them. Now, we must also address the geopolitical elephant in 2026. We are, we are in a fragmented world. The United States, Europe, and China are all racing to secure their own supply chains for critical minerals. But the reality is that much of the world's lithium is concentrated in South America, cobalt in the Democratic Republic of Congo, and the nickel in Indonesia and Philippines. When we force a 100% transition to a technology where one or two nations control 80% of the mineral processing, we are surrendering energy independence. We are creating a new OPEC, not of oil, but of minerals. And just as we land with oil dependency, that is a vulnerability we cannot afford. A 2026 report from the Critical Mineral Strategic Intelligence Initiatives warns that without significant diversification of supply chains and recycling infrastructure, the world faces severe supply constraints for lithium and cobalt by 2030. The report notes that current recycling rates of lithium ion batteries hover around 50% globally, and much of that material is processed in a few key locations, primarily in China and South Korea. The geopolitical implication is staggering. If a trade war breaks out, if a supply chain is disrupted, if a processing country decides to weaponize its materials the way Saudi Arabia once used oil, we have a problem. And the solution is not to speed up the transition to EVs. It is to diversify our approach. The hybrid reality is our strategic shield. By utilizing smaller batteries, we reduce our mineral dependency by 90% per vehicle. This allows us to bridge the gap while we build domestic sustainable supply chain that doesn't leave us vulnerable to global trade volatility. A plug-in hybrid uses one-fifth the battery of a full EV. If we deployed PHEVs at scale in North America, we could reduce lithium imports dramatically while still electrifying a significant portion of the vehicle fleet. This is not just economics, it's national security. And it is a point that is slowly gaining traction in the policy circles as people realize that the all EV strategy is, in fact, geopolitical bet on Chinese dominance of the mineral supply chain. For years, we have been told that the internal combustion engine is a fire. We need to put it out. But fire isn't our enemy. It was the first technology that made us human. We don't solve a crisis by throwing away our most mature, reliable tools. We solve it by refining them until they are unrecognizable. The modern hybrid engine is a miracle of efficiency compared to the engine that worked 18 years back. We are reaching thermal efficiencies that were once thought impossible. A modern gasoline engine in hybrid vehicle can operate in its optimal efficiency band for most of its runtime, turning off when electric power suffices and firing up only when needed. That's not a compromise, that's the engineering at its finest. Atkinson cycle engines, advanced fuel injection, variable valve timing, and turbocharging have pushed the efficiency of the internal combustion to levels that would astound engineers from the 1990s. Combined with electric motor assist, the modern hybrid engine is cleaner, more efficient, and more responsive than the crude 30 engines of decades past. Make no mistake, I have not amended the engine. I have evolved it. And that evolution is what the in between represents. Let me paint you a picture of what 2035 could look like if we embrace the in between instead of chasing the impossible dream of an all EV world. In 2035, the global vehicle fleet includes 400 billion hybrids and plug in hybrids, vehicles that are affordable, practical, and effective. These cars do not require a revolution in charging infrastructure. They plug into existing 120-watt outlets in garages and charge overnight. They work in cold climate because they have thermal management built in. They work for rural communities because they can be refueled at any gas station. They work for truckers because they maintain range and payload capacity. Alongside these, we have 100 million pure EVs concentrated in urban markets with robust charging infrastructure and moderate climates. These are not second class vehicles, they are optimized for their use case. A city dweller in Los Angeles or Dubai can absolutely live in a full EV, but we have stopped trying to force Californian solutions into a global population that lives in a very different climate and circumstances. In that vision, we have reduced global CO2 emissions from transportation by 50%, not by chasing a single technological solution, but by deploying the right solution in each context. We have reduced our vulnerability to mineral supply shocks by diversifying our technology portfolio. We have made clean mobility accessible to billions, not just to be affluent. And we have done it by respecting physics, respecting economics, and respecting the reality of human behavior. I want to leave you with one final thought. There is a tendency in our culture to see compromise as weakness. We want heroes, not pragmats. We want the bold stroke, not the nuanced solution. We want the person who says we will eliminate something completely, not the engineer who says we will optimize the system as a whole. But engineering is not about heroes. It's not about talking the world. It is and making it better. It is about recognizing constraints and working with them. It's about recognizing unintended consequences and designing them away. The in between is not compromise, it's a bridge. It's the most radical, effective thing we can build. It works for the family in a rural town that cannot afford a $60,000 EV. It works for the apartment dweller who parks the car on the street and he has nowhere to plug it. It works for the trucker in the blizzard. It works for the factory worker who depends on the mining industry. And it works for the environment by maximizing the impact of every single gram of lithium we mine from the earth. Let's stop sprinting towards the horizon that keeps moving. Let's start building the reality that is right in front of us. The future of mobility isn't about leaving people behind in the same name of progress. It's about making sure the world can afford to come along for the ride. Thank you.